All right, so today's warm-up question is going to lead us into our notes for today. It says, which climber will have the hardest time holding on to the rock face? Okay, and I'm sure you can answer this just from your everyday experience without talking about forces, but I do want to talk about it in terms of forces as well. But which one? A, B, C? C. Yeah, y'all know if you're on a steeper surface, it's harder to hold on. But we're going to look at why that is in terms of the forces at play to answer the second part of the warm-up. And our notes today are forces on an inclined plane. And so we'll be taking more notes and doing some more after the warm-up question as well.
Is it because you can't apply as much force, Leslie, than
I'm going to go through the whole thing. Okay. So let's go ahead and take a look at the forces. So whenever we draw a free body diagram, and again, I'm not really doing a true free body diagram here, I'm just drawing the vectors onto the guy. Okay, but whenever you draw a free body diagram, you're going to always draw FG straight down. Every time. Doesn't matter if he's on an incline or not, the force of gravity is always straight down toward the center of the earth. And so since it's the same guy in all three of them, I have drawn the same exact length of the vector in each case going straight down. Okay, but he is on an incline in each of these. Whenever you look at what gravity does to you when you're on an incline, a portion of that gravitational force keeps you in contact with the ground. The other portion makes you want to slide downhill. Okay, and if you're not holding on enough, or if you don't have enough friction between your feet and the rock face. But we're going to be looking at components of this, and I'm going to show you how to draw a free body diagram on an inclined plane in a minute. So for right now, I'm just kind of drawing them, and we'll explain why we drew it this way in a minute. But that's A. For B, same, and then we have our normal force from the surface. For B, same idea. Again, a portion of it is going to be directed downward, keeping straight down as gravity, but perpendicular to the surface is a component of that keeps you in contact. And then there's the other component that makes you want to slide downhill. And then same thing here. You have the component that makes you want to slide downhill, which is really large, versus your contact. Again, that force of gravity is going to be broken into components when we start tipping our axis and we have something at an incline. So I have FG in each of these as a red vector. My FN, my normal force of support from the surface in each of these, is this dashed orange one. You'll notice those change as well when my surface is at an incline. Okay, and so whenever we look at this, it says, which force is the climber fighting against in order to keep his grip? Why would he fall if he lost his grip? Gravity. Okay, and so ultimately we need to look at what that gravitational force is doing. Again, portion of it, the green portion in each of these, is that kind of downhill that would make you slide in that direction, would cause acceleration that way. And then you also get contact with the surface from that gravity as well, at least hopefully you have enough of it. Okay, the force that keeps him from sliding down, why would he be able to stay on the surface? Okay, yeah, maybe he's applying a force, or largely it's going to be friction between him and the surface. Okay, if the force of friction between him and the surface is greater than or equal to that horizontal component of gravity, which is this green one right here, then it's possible for him to stay on the rock. But if he doesn't have enough friction, then he will slide. Okay, if he doesn't have enough friction between him and the surface, he will fall, he will start to slide downhill. So ultimately we need to start looking at friction. Okay, so frictional force depends on two things. The type of the surface, how slippery it is one way of describing that, but this mu, this coefficient of friction, and the normal force. Again, you guys have seen this equation before, but your force of friction, or kinetic friction anyway, is equal to the coefficient of kinetic friction times Fn. And again, the other one for static friction, you just had it basically looked the same, except it was written as greater than or equal to. But again, remember, mu is a ratio between normal force, or rather force of friction and normal force, and we always use values that are less than 1, so our force of friction is less than our normal force. And so if we look at this scenario, all of these have the same surface. Okay, and mu depends on the surface. Since the surface isn't changing, it's really the normal force that we need to look at. Okay, so again, coefficient of friction, since the surface is the same, it's the same. Because the surface is the same, the frictional force is really here going to be determined by the normal force, since we're comparing, again, these three different scenarios. He has less contact or support force on a steeper surface. You can see it. It's this orange vector. It's shorter here than it is here. Therefore, he also has less friction as well, because mathematically you're multiplying by a smaller number. And so there's less frictional force whenever you have a smaller normal force, when there's less contact force, versus this one, which would have significantly greater amount of friction. So back to our original question, which rock climber will have the hardest time holding onto the rock face? As you guys already knew before we even got into the forces, climber C, because he has the most gravitational force acting down along the rock surface, that's this green vector here, and because he has the smallest normal force and thus the least amount of friction that would allow him to kind of get a grip, if you will. So again, this is going to lead us into this, because I know I just put some vectors up there. Now, some of you maybe were okay following along, and some of you maybe were a little bit lost. So let's go ahead and take a look at our notes today. For second law at an angle specifically today, we're looking at forces on an incline. So we're looking at an inclined plane. Yesterday we looked at whenever we applied a force at an angle. Today we're looking at situations like this one, where we have a box or an object on a ramp or an incline of some kind, and we're going to do something similar. So let's talk about how to draw a free body diagram for the box on the inclined plane that's pictured below, assuming that friction exists. Okay, so forces that we need to draw. First things first, whenever we draw our free body diagram at an incline, okay, the first step in our free body diagram construction thus far has been to draw axes, an x and a y axis. I'm still going to do that. However, I am going to tilt my axis so that my x-axis is the surface of the inclined plane. Okay, so I tipped this so that this x-axis, and I labeled it as positive x over here, so that this x-axis is on the surface of this. It's at the same angle that this is. Okay, and you're going to want to do that, and you'll see why in a minute, because we talked previously about how whenever you go to write those second law equations and to do the calculations later on, everything has to be either in the horizontal or vertical directions. It has to be either on the x or y axes. And the problem is, if you don't tip it, nothing's going to be, well, except for gravity, nothing else would be on that axis. Okay, so to save you the time of having to break everything into components, it's easier if you only have to get components of one thing. Okay, so we draw our axes like this. Okay, so tip it so that you have tilted axes so that this is aligned with the surface of the inclined plane. Now, FG is always drawn straight down. You'll notice that that means it's not drawn on the x or the y axis in the grid I've drawn. Okay, because I'm on an incline, now my force of gravity is at an angle with respect to the surface of the incline. So now we have to actually find components of gravity, which you saw when I went through the warm-up question a minute ago. But first, before we get to that, let's draw the other forces. The normal force is always drawn perpendicular to the surface. Okay, so my normal force falls along my y-axis because it is perpendicular to my x-axis, which is my surface, and so it looks something like this. Okay, so Fn is going to be on that y-axis. I labeled this as my positive y, so it's in the positive direction on my y. I labeled this as positive x, since that's the direction I would expect it to slide if it were moving. All right, force of friction, it says to assume friction exists. That friction is always parallel to the surface. And again, since I drew my axis so that my x-axis was along the surface, I can now draw FF on that axis. So again, if you don't tilt your axis, you will have to get components of both Fn and Fg. As it is right now, I only have to get it for Fn and FF. Right now, I only have to get it for Fg. Okay, so it's less work if you tilt it. All right, could you do it the other way? Yes, you just have more work to do. So here is my free body diagram, okay, based on that scenario we just had. And again, I already said this, it's best to draw the horizontal axis along the inclined surface and the vertical axis perpendicular to this. Get the components of any forces that are not on the axes you've drawn. That's the same step we've always done. If it's not in the x or the y direction, we need to get components. for my force of gravity, which is the only force that is currently not on one of my axes, that means I have both an x and a y component. My x component, I'm sketching down here, my y component, of course, along my y-axis, but I can see these components of this total force of gravity, and I can solve for them once I know an angle and FG, and I can find them using some trigonometry. Okay, so SOHCAHTOA, that will help us get FGY, and that will help us get FGX whenever we go to actually put some numbers in here. Okay, I'm going to re-sketch my free body diagram though with those components drawn, because again, whenever you go to actually solve a problem, this is what you're going to be drawing on your test. Okay, you don't want to put the components on the diagram you turn in. It usually says that. You want to put the actual forces that are present. But when you go to solve it, you need the components. Okay, and so I've redrawn it over here with FGY on my y-axis, with FGX on my x-axis, and now I can see all of the forces that are vertical, all of the forces that are horizontal. Okay, before I go any further, does anybody have a question about my diagram? Because if you can't draw that, you won't be able to do the rest of it either. You have to be able to draw the diagram so that you can do the math. We're good so far. Okay. All right. So I went ahead and put the picture in the background here so you can kind of see it on top. But here's my forces, my normal force, my force of friction, my FG in the y direction, my FG in the x direction. Of course, those are components of this FG. Okay, in order to do any math, we need to know the angle of the incline. So let's talk about geometry. Okay, remember that the sum of the interior angles of a triangle is 180 degrees. So if you look at this entire inclined plane, I can see a 30-degree angle right here. And I know that the sum of this angle, and this angle is 180 degrees. But I know that this one is a right angle, which means this 30-degree angle is, and this angle here add up to 90. Okay, they're complementary angles. This would be a 60-degree angle. Also, though, if you look at my diagram, my FG right here is creating kind of a smaller triangle, if you will, right here. And this is 30. This is 60 right here, where my cursor is. This is 90. Okay, so you can go and you can figure out if this is 60, and again, this between FGY and my axis is 90, that means this right here where my cursor is 30. Okay, so the angle of my ramp, 30 degrees, also the angle right here. Okay, again, I told you we were doing some geometry today. Did y'all follow that? Yes. Okay, good. One more time. All right, so this is my, I'm going to stand up and point at it. This is my 30-degree angle. This is a right triangle right here. Okay, if this is 30 and this is 90, that makes this 60. Yes? Okay, this is also a right angle. If this is 60, this has to be 30 because they're complementary angles. Oh, okay. All right? That's just easier when you put it. Yeah, it's fine. I know, I was using the cursor because I'm recording it. All right. So everybody good now? Okay, so if you have the angle of the incline given to you, you're going to have to use a little bit of geometry to figure out what the angle is that you're going to use with these components. But it's going to match this angle. Okay, so again, that angle is equal to this angle. They're both, in this case, 30 degrees. Okay, this angle here, which I don't really need for anything, but it would be equal to, oops, wrong way, to this angle here. Okay, because again, remember the opposite interior angles formed when a line intersects parallel lines are congruent. Y'all remember that from your geometry class as well? Yeah. Okay, so there's a couple different ways you can get there. Okay, but you should be able to get there. You should be able to figure out that missing angle. Okay, so whatever way works for you is fine, but you need to use some geometry here to get there. Are there questions about that? Yes, sir. Sorry? These are my opposite interior angles, ones with the 2 dashes, this one and this one.
So they will always be the same?
Like, yeah, that's if you have parallel lines, like I drew in an axis down here. Yes.
Then which one's the incline?
This is the angle that you could technically use this one if you wanted to for your math. As long as you know one of them, you're good.
Oh, okay.
Yeah, you just have to know one of the angles. You can do it. It doesn't matter which one. Just obviously this one up here is 30, this one's 60. All right. So I'm going to use this angle here. This is the one that we typically use whenever we're finding components. If you're drawing it, this is what I'm going to do every time, is this one rather than using this one. This, as we said in the previous one, was 30 degrees. But let's go ahead and do a different, it's actually the same problem. It's still 30 degrees in this one. This problem says a 50 kilogram block slides down an incline that makes an angle of 30 degrees above the horizontal. If the block slides at constant velocity, what is the normal force and what is the force of friction? Okay, so this is similar to the type of problem that you might see again on a test or on one of your task options, okay, or checkpoint. So I have drawn my free body diagram in such a way that my x-axis is aligned with my surface of my inclined plane, so it's tipped. Okay, I've labeled the positive direction this way because that's the direction I would expect it to slide at constant velocity, and my positive y direction this way. Again, we're going to draw the forces onto this diagram starting with Fg, which is always straight down. Straight down is not on my axis here, and so I have Fg drawn like this, straight down, and in a minute I'm going to have to get some components for this. I'm going to draw Fn always perpendicular to the surface. Again, normal force is, by definition, perpendicular to the surface of the inclined plane, so it will fall along my positive y-axis. Okay, I need to also include friction because that's the only way that I could possibly have a block sliding at constant velocity, is if there was friction opposing that component of gravity, so that those were balanced. That's the only way it's going to happen. There has to be friction present, and so I have FF, and again, it's going to be opposite the direction of the motion, so I have drawn it kind of uphill, if you will. And of course, we're going to be solving for it, so that kind of implies that it's there as well. So far, does anybody have a question about the diagram? Okay. So from here, I know that my incline is 30 degrees, and here's where my incline would go. Okay, again, it looks just like this one. That angle is congruent to this angle. Okay, again, we can go through the geometry again, but we just did it a minute ago. These two angles are congruent to one another. Okay, the angle formed by Fg and my y-axis is congruent to the angle of my incline. So I know that's 30 degrees, and that's what I'm going to use whenever I try to find these two components. Again, when you find the components, you're looking for one that's along the x-axis, and the other will be parallel, or sorry, this is the y-axis. One that's along the y-axis, and the other will be parallel to the x-axis, at least the way we've drawn it. Okay, whenever I redraw it, I'll put it up here, but for now, I'm drawing it parallel to my x-axis. Okay, so again, let's go ahead and just focus on this for a minute and see if we can figure out what the x and y components are for that force of gravity. Okay, just in terms of variables for now, we're not solving anything yet. I know, again, SOHCAHTOA tells me that sine is equal to opposite over hypotenuse, and that cosine, which is what I have here, is equal to adjacent over hypotenuse. And so if I'm solving for Fy, it is adjacent to my angle, so I'm going to use cosine of my angle theta, which of course I know is 30, but cosine theta equals adjacent over hypotenuse. My hypotenuse here is Fg. Okay, it is, here's my right angle, so you can tell that's your hypotenuse. But if I rearrange this to solve for Fy, I have this. Fy equals Fg times cosine theta. I can do the same thing to solve for Fx, except Fx is opposite my angle, so I will be using sine of the angle theta equals Fx over Fg. Again, if I want to solve for Fx, I can multiply both sides by Fg to get this. So the x component of my gravitational force is equal to Fg sine theta. The y component of my gravitational force is equal to Fg times cosine theta. Okay, we can use these. In fact, I'm going to label them onto my diagram in a second, but we can use these later on in our calculations when we go to find Fn and Ff. So here they are. I redrew my diagram. Everything now is on an axis. Okay, so here is the x component of gravity. Here is the y component of gravity. This one's equal to Fg sine theta. This one's equal to Fg cosine theta. Okay, so redraw it so that you have everything on an axis, and now you can do the math. Okay, again, your second step, after you draw the free body diagram, your second step in these types of calculations is to write out those second law equations. Okay, Okay, before I get to that though, I'm going to point out that because this says we're at constant velocity, I know that I have balanced forces. So I know that Fx is equal to Ff, and I know that Fn is equal in magnitude to Fy. Okay, so I know that these have equal magnitudes, which will come in handy whenever we look at this in a second. So again, we're going to write out our second law equations. F net y equals m times a. Again, F net in the y direction is the sum of my forces in the y direction, keeping in mind that they're vectors. So this one is negative because it's in the negative direction. So I have Fn plus negative Fy equals m times acceleration in the y direction. I can rewrite this as Fn minus Fy, and that's just subtraction. Doing the same thing in the x direction, F net x equals m times a. Again, let's put our forces in here. We have two different forces in the x direction. Let's add those. Fx plus negative Ff. Again, I called this the negative direction, so I put a negative sign there. And then again, adding a negative is the same thing as subtracting. Okay, so I have these two different equality statements for my second law, but let's go ahead and see if we can solve for what the question's asking for. Starting with Fn, so let's get this by itself. Add Fy to both sides, you get this. Okay, again, the acceleration here, 0, because it says constant velocity. Okay, also, it's not accelerating vertically anyway. Okay, it's not even moving vertically, so it would be 0 regardless, but it also says constant velocity. So everything's going to have 0 acceleration. So 50 times 0 plus Fy, and I just get this, Fn equals Fy, which I didn't need to do any of that to find because I already knew that without having to show all that work. Okay, but of course if you do have acceleration, you got to do all that work. Okay, so let's do this one now. Again, we're going to solve for Ff. Okay, Ff is, again, if I want it by itself, we're going to subtract Fx from both sides. This right now is negative Ff, so let's multiply through by a negative sign. And you get this, force of friction equals negative mass times acceleration in the x plus Fx. Again, that acceleration, 0. Okay, so that 50 times 0, gonna be 0, which means Ff equals Fx, which again, I already knew because it says in the question, constant velocity. So we could actually skip that step entirely because it says constant velocity. If it didn't though, you would need to do that. You would need to put the acceleration in there and you would need to use it to figure out what that force was. Okay, so we did a lot of work for a whole lot of nothing because we already knew those things. Hopefully you knew those things too. But let's go ahead and finish this because we don't have number values yet. I know Fn equals Fy. I know Ff equals Fx. I just need now to figure out what Fy and Fx equal. Okay, so Fy, again, we determined this earlier, is Fg cosine theta. Okay, again, we did that with the trig. Fg, of course, is mg, so it's also equal to mg cosine theta. And that's where we can plug in some numbers. The mass of the block is 50 kilograms. G on Earth is 10. My angle in this problem is 30. So this is what goes in your calculator. Again, you need to be in degree mode. 50 times 10 times cosine 30, that's going to be 500 times 0.866 is equal to 433.01 newtons. So that would be your normal force in this scenario. Okay, the other calculation for Ff, again, I know Ff equals Fx, and I know Fx equals Fg sine theta. Again, Fg is the same thing as mg, so I know it's equal to mg sine theta, and that's where you can start plugging stuff in. Again, 50 times 10 times sine of 30 degrees is 500 times 0.5, which is 250 newtons. So the magnitude of my force of friction is 250 newtons. Of course, the direction of it is negative since this is positive, so you could tack a negative sign on there to report it. But that's your friction, 250 newtons. Does anybody have a question about the calculation? Okay, if we had acceleration instead of constant velocity, yeah, there's a little extra step in there, but we went through the steps anyway, so you know what that would look like. You just would have had to plug a number in instead. All right, guys, that is how you do the free body diagrams for an inclined plane. You're going to have lots of opportunities to practice it on your own in those task options and potentially in that checkpoint. So please go ahead and get your task options opened up. You have workbook practice, which again was the paper one up here. You also have the worksheet practice, which is in My Open Math, and you have a checkpoint, all of which are due on Monday. If you have questions as you are working, please let me know.